Math 1332, Chapter 2, Set Theory, Section 5, Infinite Sets, Video 3, Different Kinds of Infinity, Countable versus Uncountable. This is where some people start kind of falling off the train a little bit because we start talking about these concepts that are beyond what you may have ever seen, namely that there are different sizes of infinity. We are not going to get into all the details behind different sizes of infinity. This is just an introduction to let you know that one size of infinity might be bigger than another. We'll see. I'll show you what I mean. All right, so let's start with a pretty simple question. Which set has more numbers? Well, we've got the first set, n, which is just our natural numbers, 1, 2, 3, and 4. And a second set that we're defining is a equals the set of x's, such that x is a real number, which means it can be any decimal, and 0 is less than or equal to x is less than or equal to 1. It might be easier to visualize a as a portion of a number line. If we had a number line and here's 0 and here's 1, then a would be every decimal that you could fit between here, including 0 and 1. And I may not quite reach to 0, but that's okay. There we go. So if you were to think about putting a dot for every decimal between 0 and 1, that's what a would represent, that portion of the real number line. Now, your first instinct might be to say, well, clearly the natural numbers are bigger because they go forever to the right, forever to the left on your number line, whereas set A is just trapped between 0 and 1. But the answer might surprise you. Before we get into the details, just a little bit of historical background. If I can select this and get rid of it. George Cantor, a German mathematician who was born in 1945 and died in 1918, was one of the first mathematicians to tackle such a problem, which tells you that in the history of everything, what we're about to talk about is not that old, just barely over a century old. But prior to his work, mathematicians who were also philosophers and deeply religious believed the study of the infinite was futile and almost blasphemous, as only God could understand the infinite. In fact, Cantor's peers ridiculed his efforts. They called it a grave disease infecting mathematics, and they referred to him as a scientific charlatan, and they demanded that he be imprisoned or even worse. Luckily, we can study this without any fear of such repercussions. By the way, Cantor was not put to death for his beliefs and studies in mathematics and science, but you think that's bad? Search Giordano Bruno, 15th century scientist, and you'll realize that we've come a long way when it comes to accepting scientific study, alongside religion and philosophy, I should say. All right, there's two types of infinite sets that we're going to explore. As the name implied in the title of the video, they are called countable and uncountable. A set is countable if either it is finite, so we start counting and eventually we stop, or it can be put in one-to-one correspondence with the natural numbers. Now, we've already seen on several sets, especially in the previous video, that we're put in one-to-one correspondence with the natural numbers. An infinite set that is countable is called countably infinite. So another way to think about it is a set is countable if either when you start counting, you'll stop, that makes it finite, or when you start counting, you'll never stop, but eventually you'll get to every number that you would want to get to. Like if I wanted to get to 1,000,000, I would eventually get there by counting. Or if I wanted to get to 1,000,000,000,000, I would eventually get there by counting. Well, you would have to count really fast and pass it off to somebody else probably, because 1,000,000,000,000 seconds is a long time. But countable basically means it's either finite or we can put it in one-to-one correspondence with the natural numbers. So what is uncountable? Well, an infinite set is uncountable if it cannot be put in one-to-one correspondence with the natural numbers. Misspelled correspondence there, I'll fix it in a moment, because I think it'll unveil this. Well, let's go ahead and unveil this. Oh, clearly the set of natural numbers is countable. We'll verify that in just a second, but there we go. So clearly the set of natural numbers is countable. And why is it clear? Well, let's set up the natural numbers. 1, 2, 3, 4, forever. We'll put an N out there to represent a generic term. To be countable, you're either finite, which this is not, or you can put it in one-to-one correspondence with the natural numbers. All right, well, let's set up the natural numbers and see if we can make a one-to-one correspondence. Yeah, I think the correspondence is fairly transparent. We match 1 with 1, 2 with 2, 3 with 3, 4 with 4, and N with N. Any set can be put in one-to-one correspondence with itself using the natural correspondence, match each element to itself. And since the natural numbers can be put in one-to-one correspondence with the natural numbers, then by definition, the natural numbers are countable. What about the whole numbers? Yes, they are, because in previous videos, we already established a one-to-one correspondence between the whole numbers and the natural numbers. So throwing 0 in there doesn't change the fact that it's countably infinite. Well, what about the integers? Are they countable? Recall that the integers are the positive and negative whole numbers. So they start with some ellipses and then they pick up with negatives, hit 0, left out a comma there. And then they continue with positive whole numbers. So to show that these are countable, we would have to put them in one-to-one correspondence with the natural numbers. So let's start with the natural numbers. 1, 2, 3, 4. And you might start thinking, let's put a few more up front. And you'll see why in a second. 5, 6, and 7. And I'm not going to put a generic nth term out there. And you might start thinking, if we're going to put these in correspondence with the integers, here's the natural numbers. Do you remember the symbol for integers? We don't use it too often, but it's a capital Z. And you might think, well, we can't do it because the integers go forever to the left and the natural numbers don't. But you're assuming that when we write the integers, we must write them in order from least to greatest. And that's not necessarily true. What if we started writing the integers by starting with 0, writing 1 and its negative, writing 2 and its negative, writing 3 and its negative? Wouldn't we eventually get all the integers listed without the need to go forever in both directions? We would. We just rearrange the order. And now we can set up a one-to-one correspondence. Basically, we packed the two infinite ellipses in both directions together by alternating between positives and negatives. Now we just have the one ellipses. Now you might be thinking, well, that's kind of froofy and hand wavy, and in a sense, you're right. There is a more rigorous way to establish a connection between the natural numbers and the integers by coming up with a formula. I'll just show you part of the formula because it would be a two-part formula. The formula would say if your natural number is even, you just cut it in half. What do you do with the odd ones? Well, the odd ones are a little bit different. But for the odd ones, you would subtract 1 before cutting it in half and then take its opposite. So for example, 3 minus 1 is 2, half of 2 is 1, and then take the opposite to get negative 1. Here, 5 minus 1 is 4, half of 4 is 2, take the opposite to get negative 2. Here, 7 minus 1 is 6, take half of 6 to get 3, and then take the negative. So basically what we're doing is we're pairing up the even natural numbers with the positive integers, the odd natural numbers with 0 and the negative integers. But because a one-to-one correspondence exists, you don't have to define it, you just have to show it exists. You could say that the integers are countable. Meaning we could get to any integer that we want if we kept counting and eventually would locate any integer that we wanted to. I thought about showing that the rational numbers are countable, but I'm going to skip that. Although if you're curious, I invite you to search the diagonalization proof. Diagonal, like a diagonal in a square. Diagonalization proof that the rational numbers are countable. Remember, the rational numbers are the set of all fractions. But it's a pretty visual and easy to follow proof. But what about the real numbers? Are the real numbers countable? Well, for now, I'm just going to say no. And recall that the real numbers are all possible decimals. So what I'm saying is, if you took every possible decimal and put them in an order, there's no way you could pick up all of them. If you wrote the first, second, third, fourth, whatever order you put them in, there would be no way to get every single decimal in that set. But what about the set we started with, the set A which is the set of all x's such that x is a real number and x is between 0 and 1, inclusive, including 0, including 1. Is that set countable? And the answer is no. It's uncountable. And I'm not going to prove it right now. Uh-oh, he's foreshadowing. But in the next video, we will actually show that it's uncountable, which is really beyond the scope of this course, but I think I can present it at a level that you can at least follow the thought process and show you the power of proof in mathematics. All right, so there are some sets that are uncountable, but that means we can't put them in one-to-one correspondence with the natural numbers because they are so large that it's impossible to do that. So which set has more numbers, N or A? Well, it's kind of a draw. They're both infinitely large, so we can say that. However, the natural numbers are countable. And that set A, which was all the decimals between 0 and 1, is uncountable. So even though they're both infinitely large, and you could say that they have the same number of elements, there's an argument that A is larger because its size of infinity is bigger than the size of infinity for the natural numbers. Natural numbers, we can count them and we would get to every number given enough time. But all the decimals between 0 and 1, we can't do that. There's too many of them. So what's under here? Well, I keep mentioning that there's different sizes of infinity, and I'm going to show you two of them. They're just symbols. The size of any, excuse me, any countably infinite set is called Aleph not. Aleph is the first letter of the Hebrew alphabet, and I'm not good at drawing them, so I copied it, but it was pretty small. If I were to draw it, it would look a little more like this. I'm not very good at drawing it, but it kind of looks like that, subscripted with a 0. If you want to see what it actually looks like, you can go to Wikipedia and search Aleph or the Hebrew alphabet. And it would look, well, I searched Aleph here, and it's this symbol right here. So I can't draw it as fancy. If you were to look at the entire Hebrew alphabet, it is the first letter in the Hebrew alphabet, which is right. I know it's here, so there it is. There it is. It is the first letter in the Hebrew alphabet. It actually stems from a lot of different alphabets and ways. I don't want to say alphabets because the Phoenicians and their hieroglyphs also included an Aleph, but let's not go too far down that path. But anyway, if you're a countably infinite set, then your size is called Aleph not. Does that mean there's a different Aleph? Yes. The size of the real numbers and the set A, all the decimals between 0 and 1, is called Aleph 1, which is just written as an Aleph with a 1 subscript. Again, I'm not very good at drawing Alephs. That's my best job at doing it. It almost looks like an N subscripted with a 1. Now, you may be going, oh my God, is there an Aleph 2 and an Aleph 3 and an Aleph however long we want to go? And the answer is yes, but we're not going to go beyond this one.